All right, now yesterday we stopped at Bernoulli equation, and just remind that for Bernoulli equation, these four assumptions have to be applied. So means that you have a steady flow, you have no friction, and you're having a compressible flow, and your flow is always flowing along your control volume, right? Your control surface or your computation domain, right? This, right? So then you get this Bernoulli equation. So let's look at one tutorial question for this afternoon. This will be in your tutorial or your handout, question number 24. You are looking at a nozzle, right? You're looking at a nozzle. So with the name nozzle, you know that nozzle have a different area from one side to another side. So as you can see on the diagram here, you have surface area, bigger surface area on the left and smaller surface area on the right. And the notation you see on the screen here, D1 is the height or the length of the 2D diagram over here. It's not the, sorry, it's the diameter. Sorry, in the question it's mentioned diameter. Because sometimes in the material that we use, sometimes the D is a height, like previously we see in our water tank. So in this case, since we have a cylindrical nozzle, so D is your diameter. All right, so there's a reason why the certain parameter given. So we will use this one to calculate our area. Derive an expression for the minimum gauge pressure required at the nozzle inlet, which is here, to produce a given volume flow rate Q. So our desired flow rate is 0.02 meter cube per second. So your Q is volume flow rate. The equation for Q is you take Q equal to VA, means you take the velocity times area. Okay, yeah. So this is the equation that we're looking at, and then the evaluate the inlet gauge pressure if D is given, D1 and D2 is given in mm. So in calculation later on, remember to switch to units SI, change it to unit SI all the time. Okay, let's start solving. Okay, so we have a steady flow and there's no changing, discharging to the atmosphere. Means that we have a steady flow go through and then discharge to pressure, atmospheric pressure over here. And this is a parameter that we know from the statement. So we're given the diameter on section 1 or point 1, diameter for section 2, and then the atmospheric pressure for at point number 2. We need to find what is the pressure gauge at point number 1 here as a function of flow rate. As a function of flow rate, and we need to find what is the value when you are given the Q or 0.2 meter cube per second. All right. So governing equation. In this case, we are using the Bernoulli equation. So P divided by rho. P divided by rho is the density, pressure divided by density, plus your kinematics or kinetic energy over here, which is V square divided by 2, or we already take out the mass. If you times the mv square, half mv square equal to your kinetic energy. So, and then GH, when you have a mgh, then you get your potential energy. Okay, then equal to constant. We recall the momentum equation again. Recall, momentum equation consists of control volume and control surfaces. And how we identify it, this is a momentum equation. You look at the content inside the integration component. You take rho times volume, you get mass. Mass times velocity, you get momentum, right? Same with this side. And the products of when you take the momentum divided by time, you'll get force. So we get force on the control volume, force for the control surface here, right? Because you time all these terms together, you will get mv divided by time, right? Momentum divided by time. So we recall all the assumption that we have for this case. We have a steady flow, we have incompressible, we have frictionless flow, and our flow is along the streamline. In this case, our elevation here is the same. If you look at the diagram, the location of this solid line is horizontal, and the z doesn't change. The elevation doesn't change. So our z point 1 equal to z point 2, and then we have a uniform flow along the streamline. Okay, so again, at least minimum criteria for our Bernoulli equation: steady flow, incompressible, frictionless, and also our flow is along the streamline. These are the four important criteria. And then this assumption 5 and 6 is from the question itself. So since we have a steady flow, so you write this equation out, momentum, and then you add in the arrow plus the small note steady, you get another 2 marks here. So equation 1 mark, the arrow is 1 mark here. So again, these are all the 3 marks portion. So make sure you go and score it. Okay, very easy to get marks there. All right, now after that, we apply the Bernoulli equation for both points, meaning it's quite easy, where you just repeat this equation for point 1 and point 2. So you take this Bernoulli equation, you put on the left-hand side, which is point 1, and then you put the Bernoulli equation on the right-hand side for point 2. So you just put in the notation. 1 refer to point 1. Those sub-note here, number 2 here, refer to point number 2. Here, and then after you get the Bernoulli equation for our streamline or for our case or for our system here, then you apply the boundary condition that we know. For example, quite direct one is the elevation. So the elevation is your z. So means your z is the same, so you can cancel out. Right? Then after that, you just simplify the equation. Most of the time when we try to use governing equation of the Bernoulli equation, we either find pressure or we find velocity. Okay, so we just rearrange what you have in the second line of the equation, like what you see on the screen here. You will get the third equation on the screen. It's just a simplification. And why I remove the notation under the row? Because the row is the same for both points. And for Bernoulli equation, the density will always same because it is incompressible scenario. Okay. Of course, you can write row sub 1 here, row sub 2 here. You can write that. But because of the assumption that we have an incompressible flow, then your row is the same. We continue with the equation. So you substitute what you know for point number 2. Pressure at point number 2 is your atmospheric pressure. So you just substitute what you know or what is given there. So the hints why we know that P2 is P atmosphere is that in the statement just now, the statement say that this portion exposed to atmospheric discharge to let me see. Yeah, you see the first line here is say that the horizontal nozzle discharging to atmosphere. It means another meaning is just say that this point, the pressure you use over here is atmosphere. Okay. All right. Any questions so far up to this slide?
No, sir.
Good,
no,
huh? Oliver and Amir, okay. And cool. All right. Okay, no question. We move on. And just a side note, when we take the P1 minus atmosphere, we get gauge pressure, yeah. So if we take P pressure, the different pressure minus atmospheric pressure, we get gauge gauge measurement. So whatever you use a sensor to sense that particular pressure, let's say you install a sensor over here, a pressure gauge here. You install a pressure gauge here. The reading on the pressure gauge is actually, it takes the atmospheric pressure, it takes the pressure, the total pressure or absolute pressure minus the atmospheric pressure. Then you get gauge pressure. Okay. So this is what we want. This is the equation that intended to find. So we want to find what is the gauge pressure equation. So P1 gauge equal to rho divided by 2 and the square of your velocity. Okay, so in exam, if you're asked to find the pressure gauge or gauge pressure, you can write P1 gauge, G-A-G-E. You can write the full one. Yeah. So, but anyway, by the way you write, we can understand what you're writing. So as long as you write something that we can relate to the question, then we'll give you marks. Okay. But you don't give us something that we hard to relate. For example, if you write 1C, something like that, or you give something 1Q, then I will put a question mark. What is all this? If you ask about gauge pressure, you write PG, then we still able to relate because all this information are given in the lecture, so we can relate to all this common use notation. Then the next is just application of what we have. The next one is the finding the Q. So applying the continuity equation. What I mean by continuity equation is the m dot is a mass flow rate for the continuity equation. When you see the continuity equation, it means that you're finding m dot. M dot is rho AV. Take the density times the area times the velocity, you get mass flow rate. Just a hint for your coming assignment. I will give you some statement in the question that, for example, use the continuity equation to solve or to find something in your assignment. It means that you are using m dot equal to rho AV equation. Take note, so or in any in test or in exam, when you see there's a request from the question asks you to use or apply continuity equation, it means that we want to see whether you understand what is m dot, what is mass flow rate, or what is the continuity equation. Yeah, continuity equation basically is m dot. Yeah. So by applying what you have, m dot, so of course the equation you see here is momentum. This is momentum, is not the momentum equation. You can write the continuity equation without the v over here. Okay, without the v, then it becomes a continuity equation. So you look for point 1 or inlet and point 2. Point 1, point 2. So you input rho AV, and you must know why there's a negative there. Why there's a negative there? Because when you write the continuity equation, there's a products of v dot dA, the vector. Okay, so there's a negative sign there. Yeah, so be careful. Okay, again, be careful on the negative sign. So we get a negative because the vector of your area and your velocity is opposite direction. That's why you get negative for section 1. You get positive for section 2. Then from here, because we are having an incompressible flow, you can take out the density in the equation. So we have V1 A1 equal to V2 A2. Any question? Any question? Anyone? No, huh?
No,
Able to understand, huh? Able to understand why suddenly become we can get V1 A1 equal to V2 A2. Huh?
yeah.
Okay, we continue. Then we write what question want us to find. Question want us to find is Q. Q actually is V times A. Okay, Q, our flow rate is V times A, velocity times area. You get flow rate. So the flow rate is the same from 1 to 2. So we can continue to come back to this equation here. And we write what we know. So this is the equation we derived just now for our gauge pressure in terms of rho V square. And we know that mass flow rate is the same when we apply the continuity equation. Okay, when we apply the continuity equation, we find that the mass flow, the flow rate Q is the same for 1 and 2. You rearrange that, you put in terms of V1 square, you just rewrite this equation, mathematics rearrangement. Yeah. And then you take what we know from other side, with this side, the ratio of your V1 divided by V2 equal to area. And your V1 equal to Q divided by A1. Because your Q, this is your Q. This is also Q. Right? Yeah. So Q1, Q2, but both Q is the same, so you can write Q for your V1. Then you substitute back into this equation to write in the Q form. Yeah. So it will take some time to understand from this stage to this stage. Yeah. It's just a rearrangement of your mathematics equation. So at the end, you arrive at P1G equal to rho divided by 2 Q square divided by A1 square, and then this one in terms of area square. We just remove the velocity term in this line into Q and A. We just flip the equation to Q and A through the conversion of continuity equation. It is your Q. Q equal to VA, and then we get this ratio, and then we change it accordingly. Okay, so this is one of the mathematics skill that we require you to show us, either in assignment or test or exam, that you know how to convert or relate to other parameter. In this case, we ask you to relate velocity and Q and the area. Okay. So once you get this term, you can substitute lah. Okay, you can substitute to the D parameter, because in the previous equation you have QA area, but in the question you are not given the area, so you are given the diameter of the cross section. So you just again you flip, you rewrite the equation again in terms of diameter. Area equal to pi r square or pi d square divided by 4. You substitute inside there, you change the equation from Q A term to Q D term. Flow rate area to flow rate diameter form. And the your exponent here, remember to change when you rearrange the equation or substitute another term there, because your area equal to pi d square. There's a square there, so when you have a square there, all right, you have a pi d square inside the bracket here. When you square it, remember to expand it in your answer. So these are the area where students will make mistakes. They will forget to carry the exponential number here. Okay, and here also. Yeah. So be careful. These are all the careless mistake in exam. Then you substitute all the value. I will not do the substitution for you. You can do it, and then this is the answer for this question. All right. So pressure gauge for this tutorial question will be 800 something megapascal. Okay, it will be 819.776 megapascal or something near to 819. Or if your answer is 820 point something, also correct, because you are doing some simplification in the decimal place there. Okay, so for this module, maximum 3 decimal place, minimum 2 decimal place for the answer. Okay, so any question for this tutorial question?
No, sir. Clear.
Clear?
No, sir.
All right. So if no question, we will go a little bit more. Is that all right? Do you guys need any rest?
No, it's okay.
No, sir.
No, sir.
Okay, we continue. The next slide, we have to go into what is static pressure, what is stagnation pressure, and what is the dynamic pressure. There are 3 types of pressure. And this 3 types of pressure is important for your lab report and also when you do a higher calculation later on. Okay, we recall Bernoulli equation, which is P divided by rho plus V squared divided by 2 plus GZ equal a constant value. This is a Bernoulli equation. So in a Bernoulli equation, the pressure that we have here is commonly known as static pressure. Okay, so Bernoulli equation, inside there, the pressure they use is called static pressure. And how we do it? How do we measure the pressure? So this Bernoulli equation is important when you have apparatus that measure pressure. Either you use wind tunnel or you use the water pressure to measure. Okay, so you have to differentiate. You have to know how to differentiate what is static pressure. Okay, so I'll give you some diagram that you see. This diagram is available in your handout also. Available in question 25. There are 2 ways we measure static pressure. The diagram that you see on the screen here on the left, which is labeled as wall pressure tab there. So wall pressure tab there, there's a gap here and the flow is flowing along the surface. So the pressure that we measure here is a static pressure. Okay, we have a hole and then we install a sensor over here. The pressure that we measure at this location is static pressure. Another method we measure static pressure is using this apparatus. We call it, there's a name for this apparatus. Or it's a static pressure probe. Static pressure probe. And you see that the flow is from the left-hand side and then parallel to the hole here. Parallel to the small hole here. Same concept like the wall pressure tab. All right, the flow is flow over the hole here. It parallel to this hole here. All right. So you can either make a tube and then there's a hole that parallel to the measure the flow that is above it. Then the measurement you get is pressure, static pressure measurement. Okay. Then another one is this one, the one that you see on the left hand side, the static pressure probe. There's a probe there. So this pressure probe normally you will see in the aircraft, a small aircraft or a big aircraft also have. There's a tube that coming out from the side of the either the wing or on the nose of the aircraft. And then this apparatus is available in wind tunnel when you want to measure the static pressure for the experimental setup. Again, so you have to be careful when you define static pressure, and you look at the setup of the apparatus. Then from there you know what you're measuring, because we are looking at three types of pressure here. We look at static pressure, stagnation pressure, and dynamic pressure. We look at the first type of the pressure. So the second pressure will be stagnation pressure. The word stagnation means there is no acceleration or there is no velocity. There's no velocity. Means you slow down the flow until it becomes zero. Stagnation means doesn't move. The air doesn't move. Okay. So what is the equation to get the stagnation pressure? Yeah, we make some modification on the Bernoulli equation. We ignore, the first step is that we ignore there's any change of the elevation, means that the measuring point that you measure is same. All right, the Z that you measure is same, 0.1 and 0.2 will be the same. So you take out the Z component, this one. Then you arrive at P divided by rho plus V squared divided by 2 equal a constant value. So stagnation pressure P0 is when your velocity becomes 0. In the equation here, when you write P0 or P0 here, means that the velocity is 0. We can rewrite the equation. So you know that Bernoulli equation, you always comparing two points. 1 point on the left, 1 point on the right. So this equation, we can write one side is for the stagnation point, one is for the point that you want to measure. Okay. So we change the Bernoulli equation into this form. And how you get this form is that these two measurement point, you are having the same elevation, means either at the same axis, the same horizontal axis. And yeah, this is just a mathematical model. So when you have a stagnation pressure there, the velocity V0 here or V0 here is 0. So you can cancel this one. Then you can rewrite the equation. You cancel. You move the row to the left to the right hand side. That you cancel this row when you move to left hand side, and then you add one row here. So what you get is that you get P0 or your stagnation pressure equal to P plus 1 divided by 2 rho V squared. So this is a mathematical model for stagnation pressure. Okay, so from this slide, you're able to see how we derive the stagnation pressure from Bernoulli equation. What are the assumptions? What are the location? What are the assumption here is that elevation is the same. There's no difference in elevation, so we take out the Z. And then we just pull out the Bernoulli equation by comparing 2 points. 1 point is without any movement of your fluid, it is V equal to 0. Left hand side, your V equal to 0. Then you rearrange the equation, you get the mathematical models for stagnation pressure. Okay, quite direct. And then from the stagnation pressure equation, on the right hand side, you see half rho V square. Half rho V square we name as a dynamic pressure. Half rho V square is dynamic pressure. So from today onwards, we will identify half rho v square as dynamic pressure, because later on you will learn about lift and drag. Sometimes I won't write the equation out. I will just mention dynamic pressure, then you know dynamic pressure equal to rho divided by rho v squared divided by half. So this one. Just for hints or information for your incoming assignment, you need to find the drag force on the body. So for your information, if the force is parallel to the object surface here, it becomes a drag force. If the force is normal or perpendicular to the body here, it becomes lift. Yeah? Just some information for incoming assignment. Yeah, because we haven't reached the lift and drag chapter yet, but we are using the concept of momentum and continuity equation to solve drag question. Okay, so just add on information for your assignment. Yeah? Drag is parallel or x-axis forces. Lift is y-axis forces. Or when you solve the assignment later on, you can put drag equal to fx. Yeah, lift is not in your assignment. So what is important is that you see the instruction it asks you to find drag force. Is basically it just means that to find your fx component force. Okay. Yeah. Okay. For your assignment done. Yeah, this one is the stagnation pressure. P is the static pressure. Okay. So from this equation itself, you know which one is static pressure, which one is dynamic pressure, which one is stagnation pressure. And then again, stagnation pressure, static pressure is always appear in Bernoulli equation. Huh? It is this one. The Bernoulli equation, the P there is static pressure. Yeah. And from stagnation pressure equation, you can find the velocity by rewriting the stagnation pressure. Right? You can solve velocity at a certain point. If you take point 1 and point 2, and you know that point 1 is stagnation point, then you can find the velocity inside the system. Yeah. So it's given by V equal to square root of 2 stagnation pressure minus static pressure divided by rho density. Okay, let me see the slides. Okay, I give you some measurement. So how do we measure the stagnation pressure? So if you look at the diagram that you see on the screen here, it's a little bit different from the static pressure just now. If you want to measure stagnation pressure, you measure from the hole directly from the flow. The flow will go directly into this small hole and it will capture the pressure. The pressure captured by this configuration or by this setup, you are measuring stagnation pressure, right? You are measuring stagnation pressure. Okay. Again, there's a difference between stagnation pressure measurement and static pressure measurement. This one. This is a static pressure measurement where you can see that the flow is along the hole here. It's along the hole here. So if you put a hole, if you open a hole in front here, and then you measure the pressure from this hole, then you will get stagnating pressure, P0. If you measure from this hole, directly from the flow, if you measure from this side hole, then it becomes static pressure. Clear? All of you clear?
Yes.
Okay. So this is is also important for your lab report later on. Yeah. So don't ask me this question anymore. When the question asks you to solve for static pressure or read the static pressure reading, or in the video later on, the reading you see, don't ask me whether, hey sir, this one is what? This one is static pressure, this one is stagnation pressure. I'll show you the setup for the experiment. You use the information that we share today. You go and define what is static pressure, what is stagnation pressure. And then from there, you calculate the velocity inside the system and so on. Okay, yeah, this is just a direct comparison from side to side for the stagnation and this one is a combination. This picture that you see on the screen here is a combination of two systems. So again, this system is static pressure measurement. This one is static. This one is the this one stagnation. Yeah, this one is the stagnation that directly measure the flow in flood. If you have a hole, means it's a static pressure combination, and you channel these two reading to the your DAQ system or your computer PC, and then you'll see two reading there, right? Two reading there. Okay, one is for static pressure, one is for your stagnation pressure. Okay, so other side also same. It's only the different setup. So if you measure from point B, you get a stagnation pressure. If you measure from the side of the tube, which is same with the hole here, you'll get a static pressure. Okay, yeah. So be careful when you measure pressure. Okay, we stop our lecture here. Let me stop the recording.